Okay, thanks, Jamie, and thank you everybody for coming this morning. Today we're going to be talking about steam condensate collection. This is a technical presentation regarding steam condensate collection equipment, design considerations, and the importance of collecting condensate for energy conservation. My name is Chase Bean. I'm the Director of Engineering and Business Development for Steam Management. My email is there. I wanted to point out, and I'll have this up again at the end, but if you would like a PDH certificate from the presentation, what we typically do is you just email me and we'll send that to you afterwards. So for that, and we'll send that out. So the learning objectives today, Jamie, can you hear me?
I can hear you fine, Chase. I've admitted a couple of more participants. So for those who just joined, Chase Bean is presenting today a discussion around the importance of collecting condensate and the energy conservation associated with that. And you'll be able to see Chase's contact information at the end of this presentation. You can send him an email directly to request a PDH certificate. Thank you.
Yeah, thanks, Danny. Sorry, sorry everybody. My sound was sounding a little off. I wasn't sure if something got disconnected. Anyway, thanks for bearing with me there. So today we're going to talk about. I'm going to do an introduction regarding steam condensate. Talk about the importance of collection, talk about key components and system design, efficiency improvement opportunities, some maintenance and troubleshooting, and then available utility incentives. And then we'll give some time for Q&A at the end. Also, we'll have a couple of stops where you can ask questions. Jamie's going to moderate those. Again, he said you can put them in the chat or there's a Q&A tab. So either one of those options, he'll be keeping an eye out for those. So what is steam condensate? Steam condensate is formed. It's a formation is the process by which steam turns into its liquid state due to a decrease in energy. So this happens usually through energy used in the process. So the steam users in the system are taking heat out of the steam and it is dropping into condensate or heat loss to the ambient surroundings. So, throughout the distribution system, you're going to have some heat loss and some condensation, assuming that you're not covering that with superheat. This is the process in a nutshell. The steam heating system process. This is not for power generation. There's no turbine in here. But so we start out with the pumps. This is the system pressure source. A lot of people don't think about it like that, but your boiler is not providing pressure to the system. It's providing the phase transfer into steam. Your boiler's pressure comes from the boiler feed pumps. They feed the boiler. There you create steam. That goes to your distribution. There's some losses there through your drip legs and or through ambient. You're getting losses, and then the condensate is collected in your drip legs, and that's sent back to the deaerator. Then you go to your energy usage. So that's your different steam users. And more condensate is formed. And all of that is collected and returned as much as possible. You lose some more through flashing in your collection tanks and leaks and other things. But and then, of course, some of the steam is some users consume steam. So you lose steam that way as well. And then that feeds into your deaerator. And any steam that is lost in the system has to be made up with makeup water. So this is where the importance of condensate return comes in. How much can you get back to your deaerator or your feed water heater and reuse for the boiler? So what's the energy impact? Steam, this is 15-pound steam, has an enthalpy of 1164 BTUs per pound. So the condensate from that steam, assuming 180-degree temperature, which is kind of a typical return temperature once you've dropped down to atmospheric is about 150 BTUs per pound. The makeup water, assuming 50 degrees, is 20 BTUs per pound. So every bit of makeup water that comes in is cooling off the system compared to returning condensate, which still has some good energy left. So every pound of condensate collected and returned, there's 130 BTUs saved compared to using makeup water. So comparing 130 BTUs for the difference between steam and condensate, that's about 7.8 pounds of condensate would be equal to 1 pound of steam. So here's an example. So we have a 300 horsepower, 15-pound boiler operating at full load during, about half the year. Well, a little over half the year, 5,100 hours. The condensate collection system is improved, resulting in 20% additional condensate return for the system. So the math there, we have 300 horsepower times 34.5 pounds of steam per boiler horsepower. That's 10,350 pounds. 20% of that is 2,070 pounds per hour. Then you multiply it by the 130 that we discussed on the previous page, 130 BTUs per pound, 5,100 hours per year, 1 therm per 100,000 BTUs. A fuel cost of $1 per therm divided by the boiler efficiency, that is $16,146 a year in savings. This is only 5,100 hours per year, only one 300 horsepower boiler, and a pretty good efficiency. So there's actually some significant savings here and could be far greater than this for larger plants. And that is just fuel savings. So water savings, every pound of condensate collected and returned represents a pound of water savings. So you're paying water and sewer for the actual water, regardless of energy content. And so that's another $21,000 per year in this example for a $2 per 1,000 pound water and sewer cost. Other savings, you have water treatment. That's actually another big savings there, but every bit of makeup water that goes into the boiler has to be treated through some mixture of clarification, softening, demineralization, oxygen scavengers, and other methods, and that costs money as well. There's also feed water pumping power. So the rest of these savings are associated with a reduction in boiler load, which comes from collecting condensate. So you reduce the boiler load, you reduce the feed water pumping power required, combustion air fan power, any maintenance associated. Then you have, like, for large solid fuel boilers, larger boilers, you have ash disposal costs. And then there's also environmental emissions controls like SCR. There's emissions controls that are consumable, like a selective catalytic reduction emission control. There's also mercury controls that are consumables, and so those are a cost, as well as electrical or any other costs associated with operating emissions control equipment. Other benefits, reduced carbon footprint. Obviously, that always comes with energy savings. Another big one people don't think about is increased system capacity. So there's a lot of plants that are out of capacity, and that's limiting their production. But if they are able to save energy required in their deaerator due to having to heat that makeup water, that gives them available capacity. And we've run into that before. So a lot of our projects are based on energy savings, but in this case, you would have increased production ability in an industrial setting, or that could also be something in a commercial setting, possibly. So that's something to keep an eye out for. Then you have increased equipment life due to improved system water quality and reduced system downtime or water shortages are a concern. So I did a condensate collection project for a food manufacturer in Ohio, and the driving factor there was that they had to stop production when they hit their water limit for the region. So it's a water constrained region, and they were interested in being able to conserve water so that they could have more production continuity. So that was way more of a concern for them than the actual energy savings that we attained. And why not return condensate? So it's always a cost and benefit analysis. What is the energy say? What are all these savings that we talked about? What's the potential there versus, you know, the implementation or even the original installation cost? And then what hurts the potential? So contamination of the condensation through the process, excuse me, is it adds to the cost of processing the condensate for reuse. So you might need polishers or chemical treatment to reuse the condensate, and that's eating into your savings. Steam is also sometimes consumed in the process, so you can't return it. It's just injected into the process or used for humidification or whatever. And so that obviously can't be returned. And then another reason is a significant distance between steam generation and use. So by the time that condensate is returned over, you know, a long distance, you're losing heat to ambient, and that distance also drives up installation costs. So I have been in projects where there's a brand new steam system being installed, and they never plan to return the condensate because it just doesn't make sense financially. Questions on the importance of steam condensate, and we'll move into key components and system design. Did you see any questions, Jamie?
No, there's no posted questions yet, but anyone is willing, or if you'd like to raise your hand or just ask a question, please feel free to do that at any time.
Yeah, thanks, Jamie. Key components and system design. So we'll talk about condensate collection points, steam traps, condensate piping, condensate receivers and tanks. There's vented. That should be vented and pressurized, sorry. Condensate pumps, heat exchangers, controls and instrumentation, and insulation, and some safety devices. First up, condensate collection points. So these are obviously you're going to get condensate at any process discharge. So any heat exchanger in the system or other heat user that forms condensate, that's obviously a collection point, and you're going to have a steam trap there. In the photo here, we're showing a drip leg. So this is on the distribution. These are basically collection pots made out of just a pipe that allows condensate to get out of that main steam line and be discharged through the steam trap. So these are recommended at certain points all over the system to remove the condensate. Steam traps. So steam traps are vital components that remove condensate from the system. There are various types of steam traps, including mechanical, thermostatic, and thermodynamic traps, each designed for specific applications. They always have four functions. One is to remove condensate. One is to remove air. The third is to close for steam. So you can remove condensate and air with an orifice, but an orifice doesn't close for steam. And then the fourth is to balance the system. So it provides a consistent pressure throughout the system. They kind of act as balance points. Condensate piping. So there's four main categories for piping. There's a drain line to the trap. So that would be either from the heat exchanger or from the drip leg to the trap. Then you have your discharge line from the trap. Then you have a common return line. That would be where several trap discharge lines collect together. And then a pumped return line would be if all those discharge lines go into a collection tank. Downstream of that, you have a pump set. And the pump discharge would be the pumped return line. And all those require different design considerations due to different pressures and temperatures, as well as flash steam percentages. So the steam trap type, this is a key component of the condensate piping design. Fast acting traps such as thermodynamic or inverted bucket traps will introduce flash steam into the collection system. They don't really allow for subcooling of the condensate before it's discharged. So as soon as it goes through that trap, that condensate is flashing. And so you have to design the piping for that to accommodate the extra velocity there. Configuration, you have to account for that flash steam. You're looking at fluid velocity, and you're looking to make sure that any joints are, like for trap discharge lines into the common header, that you're properly configuring those so that you're avoiding any steam or water hammer conditions. Material selection, you're looking for materials and thicknesses that are suitable for the temperatures and pressures that that segment will be exposed to, also considering resistance to corrosion. Most common materials are carbon steel and stainless steel. Sometimes people will use copper. Not always appropriate, but you do see it sometimes. Piping size. So the proper sizing of condensate piping is critical for adequate flow rates and to prevent condensate backup. So the different traps discharging into the condensate line can cause back pressure on the other traps, particularly when they fail and they're blowing steam through. So that's a consideration. You can try not to put the lines too close together, but also you can just size the piping larger to give adequate flow area. Slope of the line, you want the condensate piping to be sloped back towards the collection point or the condensate receiver to ensure proper drainage. 1% or 1/8 inch per foot is a typical slope for condensate piping. Proper support. So you want to ensure that condensate piping is adequately supported and anchored to prevent sagging or stress on the pipes. And that also helps maintain a correct slope so they don't get dips in the piping, and which lead to corrosion and also water hammer. And then you have expansion and flexibility. So you have to account for the thermal expansion of the pipe as it heats and cools. This is done through proper piping support selections and as well as routing design to make sure you have enough flexibility in the pipe for the different operating conditions. Condensate receivers and tanks. So condensate is typically routed to one of 4 places. So you have an atmospheric or vented collection tank, a pressurized collection tank, or a flash tank. Sometimes the condensate is routed directly back to the boiler deaerator or the feed water heater. And then sometimes it's routed to a heat exchanger for heat recovery, and then it will continue on to one of the 3 options above. Condensate pumps. There's 3 main types. There's pressure motive pumps or steam motive pumps. I usually say pressure motive pumps because sometimes they're configured where they have compressed air as a backup pressure source for startup or when steam's not available. Generally, they're going to operate off of steam, though. Motorized pumps is a typical centrifugal pump. You'll have a condensate collection tank, and then downstream of that, you'll have a pump set, and it'll just pump the condensate to the next tank or to the deaerator, typically. And then vacuum pumps. So vacuum pumps are a unique piece of equipment that basically you're pulling on the steam system instead of pushing into the steam system, creating a vacuum. This helps return condensate to the boiler. There's some advantages for using these. They can get air out of the system quickly. They can get steam from the boiler to the furthest radiators quickly or easier. They solve a lot of steam distribution problems, and they also enable smaller pipes to be used because there is more of a vacuum on the system. So you don't have as much, it's easier to get the steam out to the ends of the system, even in a smaller pipe, I guess. Where needed, they can also lift condensate from low points in the system. So that's just something to note there. The Empire State Building uses vacuum pumps to get steam, to the extreme distances and height and all, and to keep a good balance of pressure on the system. Heat exchangers. So these are typically used for pressurized condensate or district steam systems. The picture there is actually a collection tank, but if you see on the bottom, This is a coil that is heating water. So you have green coming in and then hot water coming out. Technically a heat exchanger. But heat exchangers in condensate systems are used for process heating, preheating feed water going back to the boiler, which is actually, it's useful. It actually makes the boiler require less energy to get to steam. So if you preheat the feed water, you're coming in closer to boiling in the boiler, causing less stress and thermal stress and energy use. Condensate cooling is sometimes necessary if the condensate is very high pressure and the feed water system is very low pressure. It's just beneficial to use some of that heat before you send it back to the deaerator. And then sometimes there's multiple stages where you're dropping down pressures and flashing off at different pressures for different system pressures that the facility may have. Generally, for a lot of systems, I should say, the main goal is going to be just collecting the condensate and getting it back to the deaerator and conserving that heat. So sometimes it does make sense to use a heat exchanger and use the heat for something else, but often you just want to conserve the condensate and all that heat is utilized in the deaerator. So some other components, controls and instrumentation. So process transmitter data, especially flow, temperature, pressure, tank levels, that can all be trended and tracked to analyze condensate return system performance. We run into this a lot when we're implementing efficiency measures, all types of efficiency measures. We want to know what the impact on the system is. And one of the pieces that's often missing is the actual condensate that's making it back to the deaerator. And it's a very useful piece of information for evaluating savings. So this is actually a flow meter that we just recently installed at a hospital. You can see in the picture there, it's not even wired up yet, but this is going to give us some insight into how much condensate they're getting back to their system and the potential for savings on other measures that we're looking to implement. Another good piece of instrumentation is steam trap monitors. So steam trap monitors can help prevent unwanted steam losses. It's basically it monitors the functions of the trap. So it'll tell you when your trap has failed, and you can address that and prevent energy loss. And we'll talk some more about that later. Any questions on key components?
There's no questions in the chat or the QA, but if anyone had any questions, please feel free to speak up.
All right, thanks, Danny. All right, we'll keep moving. So now we'll go into some improvement opportunities. So here's an obvious one, is insulation. So if you can keep your condensate hot, then you're conserving energy, which can be reused in your deaerator or your heat exchanger, or wherever you're recovering that energy from your condensate. A reduction in heat transfer is about 90% reduction can be expected from a good insulation job compared to bare surfaces. It also helps maintain system consistency. Again, you're reducing your carbon footprint, and you are also creating a safer environment for your workers by minimizing heat-related hazards. Safety devices. That slide got moved, sorry. That should have been in the key components. But safety devices are important. This is showing a bank of safety relief valves on a steam header. But you also have safety relief valves on your condensate collection system. And those are important, as well as vent valves and vacuum breakers to prevent unintended vacuums on the system. So sorry about that, that's out of order, but we'll go back to efficiency opportunities. Okay, so here we go. So most common efficiency opportunities are steam trap maintenance, steam trap monitoring, thermal insulation, condensate collection and return improvement, pumps, yes, pump, steam motive pumps configurations, leak repairs, those can all be improved. Capturing condensate flash steam, condensate heat recovery, and also steam vent condensers. Okay, so we evaluate these efficiency opportunities. Typically, we're going to do a heat and mass balance on the system and evaluate the impact of how much condensate, if you improve your condensate return, how much energy savings does that result in? Water savings, all the savings that we talked about before, we can plug those numbers into the heat and mass balance and really get a comprehensive picture of the savings. The numbers that I gave earlier is a pretty simplified approach as far as saying 130 BTUs per pound is saved per pound of condensate, because the system is impacted in a variety of ways. If you change any point in the system, condensate return, that's going to change your makeup water flow, that's going to change your steam flow into the deaerator. It changes your flash steam at different points in the system. So it's it all kind of affects each other. So the best way to evaluate is really to do a heat and mass balance of the system with as much information as possible, and use that. I typically use that for my savings calcs. Also, we're going to be in an earlier webinar, we did an industrial assessment. The subject was industrial assessments for steam systems. I did an example of a heat and mass balance in that. We're going to be posting that video to our website soon, so you could go back and access that webinar if you're interested in how I do heat and mass balances. Okay, so steam trap testing. So this is a good opportunity. Steam trap repairs is often the best opportunity for efficiency improvement in a steam system. Traps should be tested and repaired at least annually. Traps are usually the greatest opportunity. I said that typical fuel reduction is 15 to 30% by implementing a trap testing and maintenance program. And the main methods of testing are visual, thermal, ultrasound, and monitoring. Speaking of monitoring, here is an example of a monitoring dashboard here. This is a trap monitor. You see it's just clamped on downstream of the steam trap. This is an ultrasound-based monitor. There are different types of monitors which can be implemented for different situations, but generally the traps are going to show you your whole trap population, or at least the monitored trap population, on a dashboard, and you're going to be able to see trend the trap function over time and see failed traps. And then they'll also often have functionalities like maintenance history, layouts, and where you can see the trap location, make and model number, so you know what you need to order if you were to have a failed trap, and energy losses and savings. I should note too that some utilities provide rebates for monitoring systems, as well as enhanced rebates for repairs of monitored steam traps. So if the trap is monitored, you get a little bit extra on your repair rebate for some utilities. I do see a question, Jamie. What is the communication protocol for monitored traps? They're all different through different. So I guess let me read that more clearly so everybody knows. What is the communication protocol for monitored traps? He says Wi-Fi or wired. They're all different. Traditionally they were wired, and so the cost was pretty high for that because you're having to run wiring throughout your whole distribution system to catch all these traps, right? Now they're usually wireless. They can be Wi-Fi based or LoRaWAN based, or through a cell signal, or ours. The ones that we typically use use a cell signal through gateways, and they communicate to the cloud that way. Jamie, you have any more comments on that? I know you're.
the example you're showing is a cellular backhaul using a lower WAN network, but for instance, Armstrong uses Wi-Fi. So Wi-Fi or cellular backhaul are the two.
Okay.
And the Wi-Fi would be an independent network, so you wouldn't have to go through a firewall. You basically have to create your own independent Wi-Fi network that communicates independently of the IT infrastructure of a facility.
Yeah, and sometimes that's a benefit. Often, actually, it's a benefit because it's you don't have to worry about your any security concerns because it's kind of just its own system that you can log into and check your Steam traps, but not necessarily integrated into your control system. Although it can be that as well.
All of the systems that are available on the market can communicate with a BMS.
Yeah. Okay, so the next opportunity is capturing high pressure condensate flash steam. So when saturated condensate flows to a lower pressure system, steam is flashed off. So that steam can be recaptured for use in lower pressure steam systems. Heat and water are conserved by doing this. An indication that this opportunity is available is if you have collection tanks that are flashing excessive steam, or if you have also, obviously, if you have low pressure steam applications available where that flash steam can be used. This is generally only going to be an opportunity for higher pressure steam systems because you will have higher pressure condensate available. So the efficiency solution is to install a flash separator tank, and then the steam is piped to a low pressure user, and then the condensate comes out of the tank and continues on to the lower pressure collection system. This is an example of this in it's obviously not a new retrofit, but an existing flash tank at a paper mill that we did a project at this year, veneer mill actually. But anyway, this is a flash tank, so the steam is flashing off, being routed to their low pressure steam system, and then the condensate continues on to the lower pressure collection system. So here's an example. So we have a 6,000 pound per hour of, we have 6,000 pounds per hour of 145 pound condensate, which is sent to an atmospheric flash tank. So the flash steam is lost, and then the condensate continues back to the boiler. So the 145 pound condensate has a liquid enthalpy of 336 BTUs per pound. There's a 30 pound low pressure steam system, and the atmospheric condensate has a enthalpy of liquid enthalpy of 177.7 BTUs per pound and a vapor enthalpy of 1149.4 BTUs per pound. We have a steam cost of $8 per million BTU and annual operating hours 8,000 hours. So first, you're going to calculate the current steam loss. So this is basically you're trying to solve for the flash steam percentage here. This is the liquid coming out of the tank at 177 BTUs per pound. The liquid percentage is 1 minus the flash steam percentage. Then you have your flash steam percentage times its enthalpy. Solve for flash steam percentage and you get 16.3%. You plug that into your total, and you're getting this amount of energy lost. Then your solution is you implement a flash steam recovery tank at 30 pounds. And then basically that tank flashes less, right? So it's going to have 6.6% flash. So once it leaves that tank, the 30 pound tank, and goes to atmosphere, it's going to be 6.6% flash steam instead of 16 and change flash steam that we had on the previous slide. So you're going to calculate your new losses. Now, you should also note that there's less condensate coming out of the system there because you are using some of that condensate in the flash steam. So instead of 6,000 pounds per hour, we have 5,460 pounds per hour times a lower flash steam percentage. And now you have this as your energy loss. So your energy conserved is your original energy loss minus your new energy lost. And you have a significant savings here. Multiply that by your hours per year, and your energy cost, and it results in $45,000 a year of savings. So this is basically only for 6,000 pounds per hour of condensate. I would say most systems that have higher pressure condensate available are going to have a higher flow rate than that. So this is a very realistic project. Condensate waste heat recovery. So generally we've talked about the energy that's carried in the condensate is going to be preserved when the condensate is cycled back to the boiler plant. When the condensate return is not possible, the heat is lost. There's also situations where the user is on district steam and they are incentivized to use as much of that energy from the steam that they're paying for before they send it back to the district plant as possible. So even once they get down to condensate, if they have no temperature penalty for the returned condensate, they want to get as much energy out of that as possible. So that's another situation where you're trying to get heat out of your condensate. The indicators here are that there is no temperature penalty for the condensate. There's a high condensate drain return temperature, and there's an opportunity to utilize any captured heat. Any captured heat. This is when there's no flashing here. This is you're already at atmospheric temperature and your or atmospheric pressure, and you're trying to use just the remaining heat. So the efficiency solution is to install a heat exchanger to capture heat. So here's the example. So we have a hospital utilizing district steam. They have no cost penalty for condensate return, but they are returning hot condensate to the district plant. So they also have a steam-driven domestic hot water heater located in the same room as the collection tank. The hot condensate temperature is 194 degrees. They have about 104.5 GPM of average flow. And then they have operating hours, 8.5 hours per day, every day. And a steam cost of $20 per million BTU, which is, it seems high, but for district steam, that's actually probably a little low today. So this is a real example here. So this is the hospital that we're at. This is the collection tank here. This is the hot water heater. So we want to take condensate out of this tank, run it through a heat exchanger, and preheat the water going into the hot water heater. So every bit of heat that we are able to use, this is a steam-driven hot water heater, by the way. So every bit of heat that we raise the non-domestic cold water, that is less steam that's required in that hot water heater to heat the water. So that's the energy savings. So in this example, we have a pump that we mounted to the top of a tank. Top of the tank, it pumps out through the heat exchanger back into the tank. So this just circulates. The pump level goes up and down as these pumps cycle on and off to return to the condensate. So we have sized the inlet so that it's below the low level of the tank. So once our system is primed, this will just shouldn't affect the normal operation of the collection system, but we'll circulate this water so we can gain the heat from it. And this is the non-domestic water supply going through to the hot water heaters. We calculated that it's going to cool the condensate in the tank down to 172 degrees. We calculated that through the heat and mass balance. And here's the math for that, if you're interested. But the key point here is that we're going to have about $72,500 per year in savings for project cost of $180,000. And we are going to be, this is a real project, we're going to be commissioning this in a couple of weeks. But their savings is actually, their cost for the steam is actually closer to $30 per million BTU now. So they're going to be over $100,000 in savings once the system is, annual savings once the system is implemented. Questions on that? Again, that section was the opportunities for efficiency improvement. So any questions there?
I don't see anything in the chats or Q&A, Chase.
Okay. Maintenance and troubleshooting. So, we have, here's the list here of different things that kind of come up when you're performing maintenance, and we'll talk about some of these. But pump inspections is a big one. So condensate, we're talking about condensate pump inspections, whether they're mechanical or pressure motive pumps. The pressure motive ones are the ones that are a little less obvious that they're not functioning. And we'll talk about that on the next slide. Excuse me. Steam trap inspections, repairs, replacements, and monitoring. Again, that's always a big opportunity for efficiency improvement and should be on the top of your list for maintenance procedures. You can clean strainers and filters in the system. That's always helpful for proper operation, checking for leaks, testing safety devices, monitoring tank levels. So we always want to make sure that's one way to verify condensate flow. And we've assessed opportunities measuring just tank levels over time and calculating flow that way. So when you don't have a condensate flow meter, those tank level gauges are your friend as far as getting a picture into what's going on there. And then, of course, keep your insulation in good repair and making sure that your condensate is properly being drained out of the steam system. Maintenance and troubleshooting. So talk about some things with the motive pump testing. You want to do visual inspection. You can inspect that the motive steam is available. You want to check for any visible damage or loose connections. Gauges are in good repair, those types of things. You can check the pump with an ultrasound, actually, just like you would test a steam trap. You can listen for the pump to cycle. Often when they're failed, it just sounds like it's blowing through. And so sometimes it's not obvious that it's failed because the condensate still can flow through, but it generally is not going to flow through as well. You also want to ensure that it's everything's properly connected and condensate is flowing. You can check the steam supply, make sure it's at the correct pressure and temperature. Often the regulators for the steam supply fail, and those need to be replaced. So you might be getting too high of steam, high steam pressure rather. You can observe pump cycling, so you can often hear without the ultrasound. You might be able to hear the pump cycling. Sometimes the pumps have gauges on the side, so you can actually watch the level, watch it cycle through the pump level. So that's another way you can check. And then you want to check your condensate inlet, check valve positions, make sure everything's kind of in the right configuration. Monitor performance just through all the things that we've already talked about, and then leak inspection, which I think I mentioned. Okay, so getting into the last section here, utility incentives. So regarding condensate collection, this is usually going to be some sort of engineering study to evaluate the potential for savings. The studies can be incentivized through utilities. It's usually tied to a stipulation that any efficiency measures are implemented within a certain amount of time. So you can get some assistance with that as long as you implement the opportunity. And then retrofitting. So these are kind of custom incentive projects. So you're going to usually get paid on the therm saved, whatever rate the incentive is available to you at is usually going to be on a therm save, whether it's, could be $2 a therm, $3 per therm, something like that. And you have to make sure that you're measuring and verifying those savings in a way that the utility finds acceptable. Steam trap incentives. So these are often incentivized by utilities. Surveying, the trap surveys are incentivized. It could be $28 to $60 per trap that you get back for the survey. It may have a cap for it, and sometimes can be incentivized as part of a ASHRAE level, or as part of a comprehensive audit. So an ASHRAE level 2 would be a good example, where they incentivize if you perform a total level 2 audit, and then maybe the steam survey is part of that audit. Repair and replace is typically incentivized $25 to $600 per trap. It varies a lot. You can get prescriptive rebates anywhere in that range, depending on the size of the trap or pressures of the steam system. So that's kind of the reason for the large range, is because there is a large range of applications. But there's also custom rebates available, so you could be anywhere from $2 to $6 per therm. We've seen this year on custom rebates. Some of the utilities will have tools where you put in your trap population and your failed traps that you found, and they have certain methods that they require you to use to calculate the losses to get that custom rebate, and we are familiar with those methods, and we do that often for our clients. Monitoring, so $50 to $200 per trap for the initial install of the monitor. Also mentioned earlier, some utilities will give you an enhanced repair incentive. So once the monitoring system is in, year over year, as you have failures and they are replaced, they reward you for replacing those failures, assuming that you are, the basis is that you're repairing them more quickly and reducing your energy losses that way by using the monitoring system. And that is it for utility incentives. And that brings us to the end of the presentation. So we had about 10 minutes left. If anybody has any questions, feel free to type them in. And
we do have a question about the Efficiency Vermont's current steam trap audit offer, and I have to admit I haven't seen it, so we'd have to research that one.
I think he's actually offering some information. So he posted a.
I see it. Thank you. Got it. Okay.
Yeah. Thanks, Chuck. That's useful. Yep. And so, incentives vary by utility or even within different regions or markets within the same utility, usually more different regions. But it's a complicated thing to navigate, and we do that a lot. So I think that it's my impression that incentives for steam systems are underutilized compared to other incentives. So if you have say lighting incentives, I think people are jumping on those quite frequently, but not everybody's doing efficiency improvements on their steam systems, and they can be really good tools for improving the payback on those opportunities. Yeah, Chuck says efficiency utilities love steam savings. Agreed on underutilization. Yep. Have you worked on steam system in a paper manufacturing process? Yes, I have. In other roles, we did. I've done retrofits on different boilers, like at craft mills and other paper mills. Yeah, I've actually done a lot of paper manufacturing. But we earlier this year did a veneer mill where we did a steam control valve replacement. We replaced 14 control valves and upgraded their PLC programming in their steam system to help them protect their header pressure and some other things. It was a pretty neat project. And we have case studies on that on our website if you want to check that out.
We did a other one too for heat recovery, boiler blowdown heat recovery project at a paper mill recently too. That's
right. Yeah, we did a design for that. It was a blowdown controls upgrade and then a blowdown heat recovery system. Yeah, that was another good project. Again, so my email is there. If you want a PDH certificate, just email me there. We'll reach out to you about our next webinar. It's typically the last Thursday of the quarter, but at the end of the year, we don't do that because it's a few days after Christmas or around Christmas time. So it'll probably be into January, but we'll announce that date and correspond with all of you about that. But again, and I'm still hanging around for questions, but for anybody that's jumping off, I just want to thank you for attending, and hopefully you found the presentation useful. Feel free to email me with any questions or for your PDH certificate. There's another question if you have.
Question here, Chase, in the message in the chat.
If you have a high pressure condensate return of 50% and you want to change the high pressure condensate return portion from an open system to a closed system, will the condensate return volume change due to back pressure? I think what you're getting at is the steam trap capacities, because they operate off of a differential pressure. So if you add back pressure onto your steam traps, it's going to reduce their capacity. So that needs to be evaluated. Most traps are sized with a large capacity margin, like the typical sizing factor is 2 times the expected load. So it doesn't necessarily mean that you're going to have to change all your traps out, but it definitely does have to be evaluated. That's a good question. Thank you. As far as your return volume, like actually getting back to the plant, your volume is going to go down because if you collect more condensate, your steam use is going to go down. So if you flash some steam off and use that, that's some condensate that's not going back, but it's also offsetting steam that's used. So I don't think that your percentage of condensate will go down, but your total usage of your steam and condensate is going to go down. Again, that's why I do a whole heat and mass balance, because one thing affects the other, and it you have to have kind of a complete balance. It's easy enough to say it's 130 BTUs per pound of condensate, but in reality, there's a lot more going on than that. Yeah, thanks for that question. All right, we'll hang around for the remaining 5 minutes, but yeah, thanks for the questions and thanks everybody for attending. I'll hang out for a minute, but if there's no other questions, that is basically the end of the presentation. So feel free to drop off whenever you want. Chuck, yeah, we definitely work in Vermont. If you have a project in mind that you would like some help on, I'd be glad to talk to you about that. That paper mill we mentioned earlier actually was in New Hampshire. So we're happy to work in Vermont. We do a lot of work in New England.
Well, I thought it was a good presentation, Chase, and I think condensate is not discussed a lot. When people think of steam systems, they don't talk about the condensate side of it, and I think there's a lot of opportunity there that gets overlooked. So I think this would be a great topic for a future discussion as we start to talk more about maybe with some industry and product specific guests on another call, we could bring this topic up again.
Okay. Yeah, that'd be great. Anybody that's listening to, we are going to, I mentioned the next quarterly webinar, but we are going to start up a another webinar series where we have guest speakers. So we're excited about that, and we'll send out news about that as well. Chuck, that's great. I appreciate the interest. I'd love to set up a call with you. I'll send you a message after this, and we can talk about that.